Dear students, in the last class we have discussed the magnetic force on a charge and Orsted's experiment in detail. In today's class, I am going to discuss Lorentz force and magnetic force on a moving charge. Firstly, Lorentz force. So, in the previous class, I discussed about one expression, that is the force on a moving charge in magnetic field. Force on a moving charge is given by Fb equal to Q times V cross B, vector product, whereas the charge moves in electric field and magnetic field. If the charge moves in electric field and magnetic field, then there will be two forces acting on the charge, electric force as well as magnetic force. Electric force is there on the charge because of the electric field exerts force on the charge. Magnetic force is because of the magnetic field producing the force or exerting the force on a moving charge. Electric force exists whether the charge is at rest or charge is in motion, whereas magnetic force exists on the charge only when charge moves in the magnetic field. So the net force experienced by the moving charge in the presence of both electric field and magnetic field is called as Lorentz force. So the net force is vectorially written F net, I write, equal to F E electrostatic force. F E stands for electrostatic force, and F B, that is magnetic force. So net force is a vector sum of the electric force experienced by the charge and magnetic force experienced by the charge. So that is equal to electric force in an electric field E. The electric force experienced by the charge is QE, and the magnetic force experienced by the charge is Q times V cross B. Q times V cross B. So this is called as the Lorentz force expression. Lorentz force expression. So in the last class I discussed this magnetic force. So electric force here, Fe is Q into E. This you have studied in first chapter itself. When a charge placed in electric field experiences a force as Q into E. If positive charge Q is a positive like proton, alpha particle, then force experienced by the charge is in the direction of electric field. If suppose charge Q is negative, like electron, then the force direction on the charge is opposite to the electric field. If the electric field like this, if a stationary charge electron is placed this way, electron, then force experienced by the electron is opposite to the electric field. Electric field is same towards right side here in the diagram, and the electrostatic force experienced by the electron is opposite to the electric field. In case of proton, if I take, in case of proton or alpha particle, the direction of the force is on this way. Okay, so that is the force experienced by proton or alpha particle also. Force experienced is in the same direction as that of the applied external electric field. So this is about the electric force. Now the magnetic force I discussed. Fb equal to Q times V cross B. Fb equal to Q times V cross B. That is the magnetic force experienced by the charge is charge multiplied by cross product of velocity vector of the charge and magnetic field B, where it is moving, where the charged particle is moving. So this is about the just separate parts of these force. So net force, in the exam they may ask, write the expression for the Lorentz force. Then you have to say this, write this expression and say all the terms, explain the terms. Whenever expression is asked for 2 marks, you are supposed to explain all the terms. So Lorentz force, they may ask for 2 marks or 3 marks. What is Lorentz force? And give the expression for Lorentz force and explain the terms. If it is a 3 marks question, first you have to define what is Lorentz force, meaning you have to give. Lorentz force is the force experienced by the charge when it is moving in combined electric field and magnetic field. Then the net force experienced by the charge by the electric field and magnetic field together, it is vector expression. It is not just adding the numbers, it is vector sum of the two forces. Fine. Then I will go to the definition of magnetic field. Okay, so definition of magnetic field B. How can you define the magnetic field in a space based on the magnetic force experienced by the charge? So the magnitude of magnetic force experienced by any charge is QEB sin theta. QEB sin theta. Now B equal to FB divided by QV sin theta. Okay, now if I choose, okay, Q equal to 1 coulomb, V equal to 1 meter per second, theta equal to 90 degree. Look at the numbers. Q is 1 coulomb, V is 1 meter per second, theta equal to 90 degree, sin 90 degree is 1, sin 90 degree equal to 1. So then what happens? The value of B equal to FB. Okay, so the definition of Tesla, if that if B is taken as 1, that is 1 Newton, okay, then magnetic field B in the region is said to be Tesla. So definition of magnetic field, that is the unit of magnetic field, SI unit of magnetic field is, okay, so SI unit, magnetic field is in a space around any magnetic body like magnet or a moving charge where the charge can experience a force. So that is magnetic field. Now definition of SI unit of magnetic field. So definition of SI unit of magnetic field. Magnetic field. So what is the definition of SI unit of magnetic field? Tesla. So this is the name of scientist actually, but I write here small t for writing the unit Tesla. So whenever it is name of scientist, we are using as, or it is given as the unit name for the honor of the scientist. In such cases, we are writing the small letter of the SI unit of that quantity, say magnetic field here, it is Tesla, and it is written as small letter t, not capital letter T. Like coulomb, we use symbol capital C, whereas the unit coulomb we write small like this. So it is also small c. Force Newton, small n we use. Same way here, Tesla. So what is 1 Tesla? When do you say magnetic field equal to 1 Tesla? So if the force experienced by the charge is 1 Newton, if FB equal to 1 Newton on which a charge, unit positive charge moving with unit velocity perpendicular to the magnetic field, then the magnetic field in the region we can say it is a 1 Tesla. So we can say 1 Tesla is the magnetic field in a region when a unit positive charge, moving with unit velocity perpendicular to the magnetic field experiences a force of 1 Newton, or unit value, unit force. Okay, unit force in SI unit is Newton. If a unit positive charge, if a unit positive charge moving with unit velocity perpendicular to the magnetic field experiences a force of 1 Newton, then the magnetic field in the region is said to be 1 Tesla. So this is the definition of SI unit of magnetic field. SI unit of magnetic field, Tesla is the unit. This is the SI unit. Okay, SI unit of magnetic field is Tesla. So TESLA bracket capital T. So capital T symbol for Tesla and unit name for magnetic field is Tesla. And we have other unit also. Okay, so that is Gauss. Name of scientist Gauss law that you heard. So the same Gauss, and G is the symbol for this Gauss, and one Gauss one Gauss magnetic field equal to 10 power minus 4 Tesla. So what do you say? Gauss is the smaller unit compared to Tesla, because to get one Gauss we have to multiply 10 power minus 4 to 1 Tesla. So Gauss is the smaller unit. Smaller unit of magnetic field is okay. So Gauss is the smaller unit of magnetic field compared to Tesla. Okay. So this also used, most of the time we use magnetic field Tesla, milli Tesla, or smaller than that 10 power we use 10 power minus 5 Tesla. The order of Earth magnetic field is about 10 power minus 5 Tesla. Means it is a very small magnetic field, but it is spread out everywhere. The value of Earth's magnetic field varies from place to place. It is not same at all the places on the equator and on the poles. It varies, and there are 3 components related to Earth's magnetic field, 3 elements regarding the Earth's magnetic field. So that we are going to discuss in the next class. So Earth's magnetic field is of the order of 10 power minus 5 Tesla, and its value roughly horizontal component we say 3.6 into 10 power minus 5 Tesla on the in India we can say, okay, not everywhere, it varies from place to place. Horizontal component means when we resolve the Earth's magnetic field into 2 components, one component horizontal component, another one vertical component. So this is about this topic. Now the force experienced by the current carrying conductor, we have seen in the previous part, that is when a charged particle moves in a magnetic field, it experiences a force, magnetic force. Now if a conductor, a metallic rod placed in a current, placed in a magnetic field, externally applied magnetic field. Remember, when a current is flowing in a conductor or rod, it experiences the magnetic force because it produces magnetic field and it is placed in the magnetic field. 2 fields are there. One is the field produced by the conductor, another is the externally applied field. Because of the 2 fields interact each other, there will be magnetic force experienced by that conductor due to external magnetic field applied. Okay. So that there will be interaction between the 2 fields. Now consider a conductor of certain length, okay, like this, a conductor of uniform cross section and having length of this conductor. Okay, so now this conductor carrying a current, so there is a current flowing. Okay, so the current is, I will take this way, and it is placed in a magnetic field. Okay, so magnetic field is applied in this region. Okay, so then there will be magnetic force on this conductor. Okay, if I put the magnetic field lines, this general, okay, so this X like this, I apply magnetic field perpendicular to the plane of the board. So this X mark indicates field is inwards. So current is there which is flowing upward and field is inwards. Okay, so then this conductor experiences a force. Okay, so now this conductor is of cross sectional area A. Area of cross section of the conductor is A and length L, and let N be the number density of charge carriers. Okay, so the force on current carrying conductor. So whenever it is placed in the magnetic field. Now N, let N be the number density of charge carriers. Number density means number of charge carriers present per unit volume. Here it actually number of electrons per unit volume, that is meter cube. Unit volume means meter cube. In 1 meter cube length, how much the 1 meter cube volume, how many electrons are present? In a metallic conductor, charge carriers are electrons. So the charge carriers are experiencing they are in a motion within the conductor. They are undergoing drift because there is a current, means there will be electric field in the conductor. Because of the electric field itself, the electrons or charge carriers move or drift within the conductor. There is another motion for the charge carriers, random motion, that is because of the thermal energy. Thermal velocity is very high, but we are telling here drift motion of the electrons, that constitutes the current. Okay, so now let N be the number density of charge carriers in the conductor. Then length equal to L and area equal to E. Length equal to L, area equal to E. So volume equal to how much? Volume of conductor is how much? Volume of conductor equal to A into L. Okay. So then how many charge carriers are present in this volume of this conductor? Number of charge carriers. Okay, number of charge carriers present in this volume is, okay, that is equal to how much? Number density into volume. So this length is capital M, so MAL. So this is the number of charge carriers present. Okay, then what is the magnitude of charge? Actually, charge on the electron is minus E. Charge on the electron is minus E. So in the direction of current when I take, so magnitude of charge flowing in the direction of current is E times. So the magnitude of charge flowing, magnitude of charge present, only charge means it will be minus E into, so magnitude of charge means NEAL. This is the magnitude of charge flowing in the conductor in the direction of current whenever a current is set up. So now the force experienced by the conductor in the magnetic field. So what is the force experienced by a single charge? So that is Q into V cross B. Okay, so Q into V cross B. So here what I can write? Okay, I can write the vector symbol only, V cross B. So here this is the general expression for the magnetic force. Now what happens? There are so many current carriers, that is electrons are moving in the conductor to set up a current I. The magnitude of charge flowing in the direction of current means, in what direction of current? Electrons are moving, drifting opposite to the current direction. Conventional current is taken opposite to the direction of electron flow. Electron flow, say downward, current is taken upward. Okay, now the force experienced by the conductor. Force experienced by all the charges present in the conductor, by all charge carriers present in the conductor is equal to force experienced by conductor. Okay, force experienced by conductor. Okay, so that equal to, that you can write F equal to, F vector equal to, F or Fb equal to. So charge present, magnitude of charge. So magnitude of charge, I said why magnitude of charge I have to use, otherwise it will be minus E. Electrons are the charge carriers, so it will be NAL into minus E. But when I write magnitude of charge in the direction of current, that will be NEAL plus positive L. So amount of charge within the conductor experiencing the force is NEAL. Okay, NEAL multiplied by, and with what velocity the electrons are drifting. So that is actually VD. Velocity is drift velocity of the charge carriers, VD. Okay, into B vector, magnetic field vector. Now you see, we have studied one expression for the current. So current I equal to NEAVD. This is the current expression, agree? NEAVD. Current expression. Whenever a current is set up in the conductor, that expression for current is this much, and hence we derive the conductivity expression in a conductor. Conductivity expression we derive. So NEAVD. So that much. So these three terms and here this one term together it becomes current. So then this becomes, okay. So area also included. NEAVD together is current. But L is there here. That current is a scalar value. So I write L, I, and I shift the vector symbol here. It is a vector. Current is not vector. Current is a scalar quantity. So I put the vector symbol for L cross B. Okay. So this is the expression for the magnetic force experienced by the conductor, and the magnitude of the magnetic force FB. Magnitude is how much? Expanding this BIL sin theta. And remember always the magnetic force experienced is perpendicular to L vector as well as B vector. Magnetic force experienced by the conductor is perpendicular to L vector and B vector. So let us find out the direction in this. So the L cross B means, in simple way, first vector, second vector. You have to curl the finger from first L vector to B vector. So magnetic field B inward, L vector direction is in the direction of current. So current is flowing this way. So L vector I treat upward. If current is flowing downward, I have to treat current L vector downward. So here L vector direction I have to assume upward because current direction I have taken upward, and magnetic field X mark for the magnetic field here indicates the direction inwards into the plane of board. Magnetic field is into the plane of board. Okay, so that's the idea. Okay, now what happens is first finger B, that is the L vector upward, magnetic field inwards. So then the force is this way. That is this way is the force experienced by the conductor. So FB, direction of the magnetic force on this current carrying conductor when placed in a magnetic field B is FB, and the magnitude of magnetic force is BIL sin theta. It is a vector, force is a vector. So it is the cross product of I times L cross B or I into L cross B. It is a cross product of IL and B vector. IL together we can take. IL together we can take and B vector. So IL cross B. I just only magnitude is there for current. There is no direction in terms of scalar vector we can't say. Okay, so there is flow direction is different, quantity direction is different. Okay, so L cross B vector, L vector, length vector in the direction of current we have to take. So magnitude of the magnetic force is BIL sin theta. Then one more fact, maximum force experienced by the conductor and minimum force experienced by the conductor. So when theta equal to 90 degree, sin theta equal to 1. In this expression, theta equal to 90 degree, sin theta is 1. That means sin theta value becomes 1 when the conductor is placed perpendicular to the magnetic field like this. This is the diagram for that. This is not the diagram for general case. It is the diagram for this particular case only. Theta is 90 degree. Okay. Sin theta is 1. So then FB is maximum. FB, force experienced by the conductor, is maximum, and that FB maximum is BIL. Maximum force experienced is BIL. So that is when the current carrying conductor placed perpendicular to the magnetic field, it experiences a maximum force. Second case is when theta is 0 or even theta equal to 180 degree, sin theta is 0, then magnitude of force FB is minimum. FB is minimum, that is 0. If it is theta 0, if theta value 0, sin theta is 0, BIL into 0, then the conductor does not experience any magnetic force. That is, whenever the conductor is like this, if I place a conductor perpendicular to the board and magnetic field also into the board, If the current goes into the board or comes out of the board through the conductor, then it does not experience any magnetic force. The magnetic force experienced by the conductor becomes 0 in that case, because why? Theta equal to 0. Then there will not be any force experienced by the charges also, because the charged particles within the conductor experience the force. Because of the charged particles experience the force, conductor as a whole experiences force. The force experienced by conductor is because of the charged particles inside drifting the force. Electrons are there, they are drifting within the conductor, so they experience the force as they move within the conductor. Due to the electric field inside, the electrons are drifting, and that electrons experience the force. Hence, the entire conductor as a whole experiences the force. So that's all about this topic. Okay, that's it.